So why do we care about signal-to-noise ratio in functional magnetic resonance imaging? And before I go into signal-to-noise ratio, I have to remind you guys that this is different from the contrast-to-noise ratio that we get in anatomical images. So contrast-to-noise ratio refers to the fact that tissue types can be distinguished from each other in anatomical images. So if we can distinguish cerebrospinal fluid or other types of fluids from actual fiber tracts and gray matter, then we talk about contrast to noise ratio. Here we talk about signal to noise ratio. And by signal we mean what is shown here on the right hand side. So that is the response of a voxel and how it changes along with the task that we ask subjects to do in the scanner. So we care about this because we're interested in distinguishing active and inactive regions in the brain. So this would likely be an active region because it shows these rises and falls in signals that are likely along with some task component that we're interested in. And you can see the noise component when it's at plateau. You can see that there's still some zigzaggedy events happening, and those are related to noise in this case. So the main goal is to detect statistically if a region is active, and detectability is directly related to SNR. If we can increase the signal to noise ratio, we at the same time also increase detectability. In any kind of model, as you may know from your statistics or econometrics courses, if you reduce the noise, then you have a higher chance to detect true effects in the data that you have. This is no different here. So detectability refers to statistical detection power or the sensitivity to detect true effects. So it's our goal to both increase signal and decrease noise. And we'll talk about this in this video. But let's think briefly about how we determine activation. Activation is the difference between signal means when the task is on relative to when the task is off, in fact. So we're comparing activation during the task to activation during the off task. And this difference obviously is compared to some standard deviation, just like in statistics. So the signal means have to be large enough, or the difference between signal means relative to the signal variability. And this allows us to determine activation. So signal to noise ratio plays into this directly because it affects the signal variability, but it also affects the difference between signal means. So statistical principles help us determine this, and let's have a look at this really briefly. Here are some examples. So this is where functional SNR is high. So let's go back to the example of when the subject was performing a squeezing task, right? So there are some periods when the subject squeezes or moves the hand, which leads to activation in the hand area of the brain, somewhere about here. And then there were some time points in the task when the subject was just asked to relax. And then we can compare squeezing to relaxation, squeezing to relaxation. And you can see that the signal to noise ratio here is relatively high, although there is quite some noise that's going on, which is probably, it looks very random in this case, relative to the rises and falls of the signal due to the squeezing. You can see that in this case, even with the naked eye, that the signal is following some kind of pattern, right? And it's not pure noise. And then when we plot activation during squeezing moments compared to activation during rest moments, we get this bar plot here, or this histogram. And we get a histogram in blue for when the subject is resting, and a histogram for when the subject is actually performing the active task. And it's quite well distinguished, right? And we can talk about these histograms in terms of their mean and their standard deviation. And then you can easily perform a statistical test on these types of histograms. And that is quite similar to a t-test. So we can then also look at a medium SNR, where it gets harder to distinguish signal from noise. You can still see some form of pattern, but the pattern is much less distinguishable right now. And this then also obviously translates to the histograms. They are much harder to distinguish, and likely the standard deviation is too large for there to be a statistically significant difference between this. This is the kind of signal you would see in regions that likely have nothing to do with hand movements, or even further here, where the SNR is very low and the two histograms overlap directly. So this gives you an idea of how functional SNR looks like and how it's directly related to the statistics that we use to make comparisons between active states. Let's go back here, it's better here, between active states and rest states, and that give us quite clearly distinguished differences in the activation patterns here. But functional SNR varies over some considerable range. Bold changes for comparisons of experimental conditions relative to rest are very large. They're typically there can be actually 1 to 5% for motor tasks, or 1 to 5% for visual activation. So I would go even higher than this. But typically they're in the range of 1 to 2. But this can go higher depending on the type of stimulus that you give. If you give a high contrast checkerboard, for instance, that's flashing, then this will lead to quite significant activation relative to rest. Now, this is a comparison relative to rest. This is not what we do in typical experiments, particularly as the experiments get more and more complex. We compare to another task that actually controls for all of the aspects involved in the experiments, the visual aspects and even the motor aspects. But we only vary the treatment task and the control task along one dimension, and that is the dimension we're interested in. I will show you an example in just a second about this. Now, when we have this, when we compare two conditions to each other, we're talking about even lower differences between the experimental condition and the control condition. So in this experiment here, the experimenters were interested in activations to faces. And this is typically processed in what's called the fusiform gyrus. And based on these experiments, this has actually come to be known as the fusiform face area, because it seems to respond more actively to faces than any other type of stimulus. And that's exactly what's shown here. So when the experimenters show the face to participants in the scanner, they see this kind of hemodynamic response. When they show something else, then they see a significantly lower hemodynamic response. This has been replicated with even inverted faces and other type of, distorted or non-phase stimuli. So this leads to the fact that we're actually working with much lower signal changes, so in the order of 0.1 to 0.5%, making our life a little bit harder, in fact. Now, why do you think is the bold response difference larger for visual and motor task than, let's say, higher order cognitive tasks? Okay, I'm not going to answer this right now, but instead I'm going to give you an overview of how these kinds of higher order cognitive tasks might look like in the scanner. So this is a slide from one of our experiments. And in this slide, we have two games. One trust game, which is actually the game we were interested in. So we were interested directly in how people make trust decisions and what the neural correlates of these kinds of trust decisions were. And in the trust game, people basically made a decision to send one of these amounts to another player B, the trustee, who would then be in the position to send some amount of money back or not. So there's betrayal involved here. Now, obviously, we want to make sure that we get specifically the correlates for trust decisions and not some form of, risk that might be involved in this kind of decision. So to get specifically this trust neural correlate we used to control game in this experiment, in which participants were asked to make investments into a lottery. In this lottery, everything was kept exactly the same as in the trust game. You can see the screens are exactly the same, except for the avatar indicating that it's a person here versus a computer here, and how much do you want to invest into B versus in a lottery L. So participants knew that they were investing in different types of one kind a person, and in the other game a lottery, but the amounts were about the same, and the motor movements were about the same, and the visual stimuli were about the same. So we matched these amounts, but we did randomize the order to keep it interesting for the participants in a sense. So what happens here obviously is that we then compare activation during the trust game to the activation during the control game. Remember that everything is matched in these two games except for this one aspect, namely that one decision is in the social domain and the other decision is in the non-social domain. So this involves betrayal, or the possibility of betrayal by another person, and this involves not betrayal but the risk to lose the investment. So obviously then what we have here is we have a very small and very specific difference between two very well-matched games in a sense, which will then lead to activations that are specific for the trust game. Now, this leads to relatively small signal changes that we work with then in neuroeconomics because of, in a sense, the specificity of the contrast that we use and the matched control game that we use. And this specificity of the difference between this condition can lead to rather small changes in signal across the two conditions in regions that are involved specifically in the trust game and not the control game, the risk game here, right? So this allows us then to identify very specific things, namely regions that are involved in estimating social risk or the risk of betrayal relative to those that are involved in estimating non-social risk or the risk to lose money. It turns out that these regions are largely in theory of mind regions. So regions that involve the temporoparietal junction and the dorsomedial prefrontal cortex. Okay, let's go back to functional SNR, specifically the topic of noise. So obviously one goal that we have is to decrease this noise, right? Because noise decreases functional SNR, which decreases our ability to detect statistically significant results. And therefore we might get false negatives in this case. And we do not want this. We want true positives. The sources of noise, just to repeat, are thermal noise and system noise. Those are things we can't do much about. That's part of the hardware of the scanner. We have motion and physiological noise. There's something we can do about motion, not so much about physiological noise like heart rate and breathing, but we could measure and control for it, for instance. And then we have non-task related neural variability and behavioral and cognitive variability. So all of this comprises noise, and that's basically the variability of the voxel intensity over time during one stable condition. And this does bad things to the data, as I'll show you in a minute, especially because the noise can be larger than the magnitude of the bold signal changes that we're interested in. And this obviously then is detrimental for trying to detect anything in our data. So let's look at these different SNRs. So this is a very high SNR of 4.0. You can clearly see with the naked eye even that during blocks when the participant is performing some task, there's much higher signal than during rest periods, right? So we have blocks here, rest periods here. Then with a signal SNR of 2, which is still very good, we have some problems distinguishing between blocks that are on and blocks that are off, right? So when the subject isn't doing anything. And this gets even worse until we get to an SNR of 0.5, where the noise clearly is larger than the signal that we can detect, or that we want to or wish to detect. And this then obviously is a situation we do not want to be in. We'd rather be in this situation where we have clear signal changes that we can also detect with the naked eye. We don't need to have this. If we have enough repetition, we can regress out the noise, obviously, right? We basically average out the noise in that case. But this is a situation we don't want to be in.